factor just happens to be n minus r, okay? So just line them up, see what you're missing, and that'll help you guys to be able to figure out what the common denominator is, okay? So, I think, and you guys might be able to correct me if I'm wrong, but the least common denominator is going to be r factorial n minus r factorial. You always pick the one that has everything in it, right guys? Like if you had a choice between x cubed and x, you pick x cubed because it has all the x's, okay?
Did you write LCD just because you didn't want to write the whole thing out, or was that?
Oh no, what we're going to do is the next step, we're going to rewrite the fractions with the LCD.
Oh, okay.
I'm just saying
I thought you were like combining.
No sir, no. This is just what is the least common denominator between all of this mess right here. So that way when you guys go home, you're like, oh yeah, that's the LCD. Okay?
Okay.
And above is how I got to the LCD. Okay? Does that make sense, Andre?
Yeah.
Okay. Let me do that on the other board just to make sure we have enough space to be able to work with this. Okay. So I'm going to rewrite each of the fractions now with r fact n minus r fact, because that is the common denominator. I'm going to carry over the original numerators from what we had. So we already had an n minus 1 fact, and then we had an n minus 1 again, I believe. N minus 1 fact. Now we have to play that game of what did we multiply by one fraction to get to the next fraction, okay? The good news is, guys, it's already done. Because if you look over there and you look what I wrote in blue, that is exactly what you would have to multiply by. It's almost like I did that to make it so painfully clear that somebody's hitting you in the face with it, okay? Does everybody see that to go from r minus 1 fact to r fact, I would have to multiply by r factorial. That's exactly why I wrote it out.
Multiplied by r, not
I'm sorry, r, you're correct, okay? Sorry, I was saying to get to r factorial. Sorry about that. So I'm going to multiply the top by r, okay? Because that's what I'm missing. We had r minus 1 fact. We need to get to r fact. So to get there, you multiply by a single r, okay? What about in the other expression? If I was to ask you guys to be able to multiply by something, okay? What am I going to multiply by to get to n minus r fact?
N minus r.
N minus r, right guys? And if you don't believe me, look right here. It's basically just slapping you in the face as telling you, what do you need to multiply n minus r minus 1 by to get to this, okay? Like I said, guys, when you go home, write it out, okay? It'll literally take you a minute to write it out, and then you guys will see what you need to multiply by, okay? Okay. Is this clear, guys? Any questions so far? Now we have equivalent fractions. This is supposed to be equal to n a combination r, okay? It looks like it's going to get there. Okay. Any suggestions now that we have a common denominator?
Add them. Hold on a second.
Well, I mean, what's the whole purpose of getting
No,
a
take
common
n
denominator?
minus 1 common. N minus 1.
Yeah, let's make it into one fraction.
Okay.
Okay, I like that. I mean, the whole purpose of getting like fractions is to be able to get to a single fraction. So, I mean, at least let's do that. Yeah. And we knew this, right guys? I mean, that was the basic process for mathematical induction. You get a common denominator to add the fractions together, right? So we would write this as n minus 1 fact in the numerator times r plus n minus 1 fact times n minus r Right, guys. Any suggestions as to perhaps now what we could do in the numerator?
N minus 1 common, right? Fact.
Yeah, isn't there a common factor of n minus 1 factorial? Okay, I mean, I would factor that out if it's a common factor. You guys can plainly see that these two are common factors. So all I'm going to do is I'm going to factor that binomial factorial out. Okay, so this is going to be n minus 1 fact. once I factor out that factorial, don't I just have three terms that are left over? What are the three terms?
R plus n minus r.
R, n, negative r. Good. So we just have r, n minus r plus n minus r. Now that's not a factorial, that just is what it is. R fact, n minus r fact. Okay, that's supposed to be equal to n combination r. Next step, almost plain as day. Guys, what's the next thing we would do?
Cancel the black
Yeah.
terms.
There's a positive r and a negative r. That's just the inverse addition property, or just equal to 0. Okay. So those go away. We are now left with n minus 1 fact times n divided by r fact, n minus r fact. Everybody okay with that, guys? Any questions about what we did to get to this point? Okay, all the algebra, we're just factoring, canceling, nothing too difficult. All right, any suggestions as to where to go now? So, Joe?
Make it n factorial on the top.
Yeah, because you have everything less than n, right? You have n minus 1, n minus 2, n minus 3, all the way down to 3, 2, 1. Well, now you're multiplying by n. So this would basically be like if I had 5 fact times 6 is actually equal to 6 fact, okay? It's the same idea. You have one less factorial and the next factor up. So this is n factorial, r fact, n minus r fact. Okay, that looks good. Yeah, that's it. Because that's the very definition of a combination, right?
Hold on, can you explain again how I get that it's, how you have it's 1 less 5 factorial times 6, so why does it just become n factorial? Why do we get rid of the
Okay.
n?
If I had,
Because wouldn't that be changing the value?
no, if I have 5 fact times 6, that's 5 times 4 times 3 times 2 times 1 times 6.
Yeah,
And
that makes
then equals, and then you can put.
So if I had n minus 1 fact times n, that's equal to n minus 1, n minus 2, n minus 3, 3, 2, 1 times n. Or,
That's just by definition.
yeah, that's the very definition of what a factorial is.
Okay.
I can move that n in front, and I get n factorial out of that. Okay? Does that make sense, Andre?
Yeah.
Okay. Yeah, maybe if you write it out and you see it, sometimes it's more helpful than just trying to sit there and try to, like, just assimilate it sometimes. Okay? All right. So guys, we've just proven Pascal's triangle, okay? Now that's, this one's a fairly simplistic proof, okay, when it comes to like doing combination and permutation proofs. For those of you guys that are going a little bit higher in mathematics, you'll have to do this with integration. You'll actually have like binomial integrals and series and things like that. So it'll be much more difficult than this, okay? This on a scale of like 1 to 10 in terms of difficulty in the grand scheme of like what you would do with this, probably like a 1.5, okay? So all the stuff that we've done before this is like a 1, maybe even a half so far. So we haven't even introduced calculus or series into these. So that's when it starts getting really tough, okay? But for right now, we're just doing the elementary stuff, okay? All right, although I'm not saying it's easy, okay? There's a difference between elementary and easy, right guys? Because I mean, obviously this is very difficult, but in the grand scheme of the scale, it's elementary level.
That's on real analysis, not on discrete math, the one you're talking about.
Oh yeah, right. But I'm just saying, like later, like in your mathematical careers, I mean, this could be much more difficult. Okay, in fact, for any of you guys ever worked with the binomial series, okay, it's a very difficult series to work with and try to do anything with. So, anyhow, all right, guys. Any questions I can answer about the proofs involving algebra of combinations and permutations? Okay, I think this is the first half of assignment 10. Which is due after the examination, although I would strongly suggest you guys work through that to prepare for the examination. As I noted on the last examination, some of you guys did really well until you got to induction, and that's just because the whole assignment 7 was induction, and guess what, some of you guys didn't work before the exam, induction. So instead of getting like an 80 or a 90, you got a 50 or a 60 or a 70 because you lost like 30 points. So you guys don't want to do that, right? Okay, so make sure you guys practice it, work on it. If you need help, come and see me for what I can do. Okay. All right, guys. So now that we know how to try to work with the binomials or some of these things with the combinations, the last topic we're
No,
going to
but we didn't prove it.
What's that?
We didn't prove this.
Yeah, we did.
this is n factorial with,
That's it.
Yeah.
oh, yeah, okay,
Yeah, that's exactly it.
Okay.
Okay, yeah, we proved it. I wouldn't lie to you, not on purpose.
Okay.
Okay, that's all right.
I forgot that, yeah.
That's okay. Yeah, that's the very definition of combination, so we're done. Okay, so guys, we looked at Pascal's triangle, we saw one of the applications was expanding a binomial, okay? In fact, I plugged it into Wolfram Alpha and I showed you that you can expand a binomial using the idea of a binomial theorem, and that's exactly what we're gonna do. So this is our binomial theorem. It's actually a binomial series. Now, we're not gonna prove the binomial series. Proving a binomial series is much more difficult than being able to prove just the combinations that lead up to it, okay? So what we did just now is like maybe about a quarter of being able to prove this guy. Okay, we're not going to prove it, we're just going to assume it's true. So if I want to expand any sort of binomial to the nth power, I have a series k equals 0 to n, and what I do is I just keep decreasing the power of the first term and increasing the power of the last term by 1, or the last factor by 1, and then multiply by a combination. Okay? This is exactly the formula that when I plugged that into Wolfram Alpha about 20 minutes ago, that's how Wolfram Alpha does this sort of thing. So if you're a computer programmer, okay, and your boss asks you to write a program that's able to expand a binomial, this is what you guys would have to do with it. And the computer just recognizes the syntax, does the spacing, and does the printing based upon that, okay? I remember in one of my last computer science classes, I actually had to write a program that output a binomial theorem. A student put in, I guess it was the nth power, we had a fixed binomial. He made it really easy for us. So, but it could be a much more difficult problem if we had to actually input the variables. So, anyway, I just want to show you guys an example of how to go ahead and expand something using the binomial theorem. Okay, so if I had 2a plus 5b to the third, okay, that's probably a problem that you guys could just do without the binomial theorem, and it would probably be just as efficient to do it without. But I just want to show you guys what it would look like if we did. Okay, so I'm going to use the binomial theorem, and I'm going to expand that binomial. Okay, not meant to be difficult. Okay, so 2a plus 5b cubed. Let me bring up the binomial theorem again too, because I want to make sure we have that. In this example, a is really equal to 2a. Okay, so a equals 2a. Okay, so that's like the placeholder for that. B is equal to 5b. And then n is going to be equal to 3. That's our exponent. So essentially, if I wanted to go through, use the binomial theorem to expand, okay, this would be equal to series k equals 0 to 3, okay, because that's our n right here. 3 combination k, quantity 2a to the 3 minus k, and then quantity 5b to the kth power. Okay, so all we did there, guys, was we just subbed in the values back into the binomial theorem. That's it. Okay, it's not meant to be difficult. It's just a straight substitution up to this point. So does that make sense to everybody, guys, as to how we substituted? We identify a and b, we identify n, we substitute. Now it's just a series problem. Okay, and we know how to work with series. We just go ahead, we keep increasing k by 1 each time. Okay, so we're going to start with 0. So the first term in this expanded binomial is going to be 3, 0, 2a to the 3 minus 0, and then 5b to the 0. Okay, so everybody sees that, guys? All I did was I just substituted k equals 0 back into our binomial theorem. To get the next term, I increased the index by 1. So now this is going to be 3 combination 1, 2a to the 3 minus 1, and then 5b to the first. For the next term, I'm going to increase k by 1 again. So this is going to become 3 combination 2, 2a to the 3 minus 2, 5b squared. And then finally, we get to the third term, which is our upper bound of our series. So that's going to be 3, 3, 2a to the 3 minus 3. And then 5b. So let me give you guys a moment to copy that down. All we're doing each time is we're just increasing k by 1. That's it. Okay? So we just start by defining what a, b, and n are. We plug it back into our series, and then we just expand that series. Okay? So any questions so far about what we've done, guys? Just basic plug and shove it. Okay? Nothing too difficult. Okay. Now we're going to compute. Okay? So we can either use our calculators, or we can just go ahead and use general knowledge. Okay. We could even use Pascal's triangle, right, guys? So we know that 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. So guys, aren't these going to be the combinations to evaluate 3, 0, 3, 1, 3, 2, and 3, 3? All right. So we don't even need our calculators, I don't think, for this. Okay. We know that 3, 0 is 1. 2a to the third is going to become what, guys?
8a cubed,
8a cubed. And then 5b to the 0 becomes
1.
1. Right, guys? So that's the first term. Okay? Does that make sense to everybody, guys? Just basic evaluation. For the second term, we know what 3 combination 1 is. 3 combination 1 is 3. 2a quantity squared now is going to be 4a squared. And then 5b to the first, that's just going to be 5b. Okay, so that's our second term. We're going to clean this up in a minute. Okay. For our third term, we already know what 3, 2 is. 3 combination 2 is 3. I just looked right at Pascal's triangle. 2a to the first is going to be 2a. 5b squared is going to be 25b squared. And then finally, guys, for the last one, 3, 3 is 1. 2a to the 0 is 1.